Thank you.
Thank you for your introduction. I'm Minoru Maeda from JAXA. I'm very happy to have this opportunity to talk to you today. I'd like to talk about automatic software update concept for software-defined satellites. Now, I'm not proficient in English, so I would appreciate if you could question slowly. We could ask questions slowly. えーそう、あれおお So, uh, I'm engaged in software research and development at JAXA's R&D department. I am working on developing software architecture for spacecraft. This time, I'll share our work on this effort. Conventional spacecraft software has three main characteristics. The first is the monolithic architecture where the entire software system is designed as a single unit to fulfill specific purpose. In other words, each software function is tightly integrated. Secondly, the software is highly dependent on the hardware. This means that the software operates in accordance with the behavior of the hardware. The third is the high level of expertise required of developers. To implement spacecraft software, developers must have a deep understanding of both hardware and software functions. These characteristics are key elements in spacecraft software, which must prioritize environmental factors unique to space. On the other hand, the expected role of satellite systems has been expanding recently, not only providing functions for specific objectives, software must be flexible enough to adapt changes in its configuration. This includes taking on multiple roles of revising its purpose after launch. Given these trends, creating a framework that enables more flexible and efficient changes on spacecraft is essential. I talk about the concept we purpose for how the new satellite software operates to resolve the challenges. The first is to enable the software to operate modularly, independent on the hardware, allowing software to be modularly interchangeable. This approach frees developers from needing to know the hardware details to implement the software. The second is to create a mechanism that enables easily software changes on orbit. This means that functionality can be changed by modifying only certain application areas after launch. This makes it easy to meet quickly to the changing user demand. The third feature is to enable the entry of industries from other sectors into spacecraft development. This opens the door for engineers without satellite systems expertise. In the coming years, this will make it possible to secure the software developers requires the growing number of satellite systems. Now I will explain how the software changes impacts satellite services. So, oh, okay. The flowchart on the left illustrates the satellite service processes using the example of conventional Earth observation. It shows the process through which the user receives the required information. The In conventional services, the system on Nobit is specialized in observe and measure. The downlink size can sometimes reach several gigabytes, which results in a large amount of data. This data is downlinked to the ground where image processing is performed and distribution is delivered. It took a significant amount of time for user to obtain the required information. On the other hand, the flow on the right shows that as the functions available on Nobit increase. Adding, adding the capacity to process image data on Nobit enables the narrowing down of the data to be downlinked. As a result, it becomes possible to quickly deliver the necessary information to the user. We really believe reshaping the system to expand the role of satellite systems within social systems is necessary. To address this, we have developed a software platform capable of implementing functions. I show a conceptual diagram on the slide. This platform can operate on general purpose Linux system like Ubuntu. Additionally, it has following three features. The first is that it enables application to run a container platform and enhances the portability of the applications. The second is that it has a mechanism to ensure the reliable operation of container application. The third is that it has a mechanism to facilitate changes to the system interface. Firstly, I explain software portability. We considered achieving containerizing the software to promote software portability. Container platforms offer advantage in software modification, flexibility, portability, and operate in a highly isolated environment. We adapted this as a framework for running software on Nobit. We provided base container for developing software that can run on this platform and define the rules of operating on Nobit. We enable developers to upload software developed on the ground directly to Orbit and run it without modification. The second is a mechanism to ensure reliable operation. Since the software created by general developer is containerized, it runs independently of computer state. On the other hand, the state of the computer must be properly monitored, and the mechanism is needed to detect anomalies. The software platform handles anomaly detection rather than having each individual software do so. Additionally, we prepare the system to ensure that general container software runs safely. And we created a recovery mechanism for the system area of the computer, which includes a function to recover the system. The third is a platform for facilitating changes to the system interface. This platform connects system components through a message hub to enable communication. This reduces dependencies between components and creates a system where changes to the interface are easier. Now, let's move on to the main topic of this presentation, how to streamline updates for this platform. In integrated system with multiple satellites connected, such as Earth observation satellite constellations, updating software services becomes a key challenge. Let's look at the case where three satellites collaborate, as shown in this diagram. Two of the three software programs are at version 2, while the third remains at version 1 due to some reason. However, the ground system sends the observation request, assuming that the satellite software version is 2. As a result, one satellite may not receive instructions, which could lead to service unavailability. We believe synchronizing software version is important to avoid these missed opportunities. Let's take a closer look at the current state of software updates and the desired state. The left side shows the current common approach to software updates on orbit. Traditionally, updates to on-orbit software have been performed manually with great care and caution. Firstly, the timing of updating software data is planned in advance based on when communication with the satellite is possible. At that time, commands are sent and the software is gradually approved. Since the available communication time is limited on each time, it may require repeating the processes multiple times, depending on the data size. After all the data is collected and the next available window is identified, the update commands are executed individually to compute the update. When this plan is applied to multiple satellites individually, it becomes extremely time-consuming and requires significant effort until everything is completed. For this issue, we believe that the automation is necessary from two perspectives in the new approach. First of all, automation of applicant processing by creating a system that automatically detects the communication availability and applying without manual command. We can reduce the need for repeated planning and manual uplink operations. The other one is automation of update process. Conventionally, we define the update areas in advance, plan the timing for communication availability, and carefully executed operations using commands. By providing a mechanism to synchronize timing, software updates can be performed across multiple satellites. Let me share the role of the software update component in our platform on the next page. We are considering a mechanism to automatic software updates as shown in the diagram. On the ground, there is a component that controls software update, while on orbit, there is a component that performs software update within its own computer. These two components work together to uplink software data from the ground to orbit. Once the uplink is complete, the update is performed at the appropriate timing by the framework. We are examining a mechanism for software updates with this very simple structure. Then we found that there were cloud services on the ground that deliver software to computers from the central system. Based on this, we decided to create a test environment. Well, briefly introduce the Amazon Web Services, which are cloud services used in this experiment. In this experiment, we use AWS IoT Green Grass service along with the open source execution environment for IoT devices. We use this service because we recognize that it was close to our concept. The following slide demonstrates how we integrated Greengrass with our framework to set up the experimental environment. For this experiment, we have created an environment that closely resembles the orbital environment with the communication satellites. Within this network, we have enabled the operation of ground-based software management services and orbital software update services. This setup allows software update to be performed through simple instructions from the ground. Since we use cloud services this time, it was necessary to design the network to adjust their features. A communication environment between the ground clouds and on-board environment is required. For this experiment, to create an environment resembling orbital operations, we collaborated with satellite manufacturers and used the network environment involving data relay satellites within the satellite management system. We also took the following two actions to create a communication environment. Firstly, we introduced domain name services. In the ground cloud service, name resolution is essential to identify the communication destination. So we have configured the DNS service accessible from the orbital environment. Secondly, we have configured data relay processing within the cloud service. For this experiment, we separated the satellite management system and the application management system to avoid any impact on the satellite management system. To perform software updates, it is necessary to enable communication from the application management system to the network on orbit. To address this, we have configured the communication path within the cloud service to perform tunneling. By implementing this structure, we registered the application in the application management service and tested automated distribution. I will share the result of the automated software update test using the structure shown on the previous page. We identified the following three items, including anticipated in advance. The first is the network speed in the space environment. The second is the network characteristics in the space environment. The third is application update timing. These were identified items in the current situation through this discussion with satellite operators. Let's take a look at each of the items identified on the next slide. The first is that the network speed. The IoT system in the ground cloud uses high-speed communication environment compared to the space environment. So in the software update, the uplink process could be completed in time, could not be completed in time, resulting in repeated timeout, and inability to update the required software. Consequently, we found that incorporating flow control tailored to the network speed is necessary to utilize this system in the space environment. The second is intermittent satellite communication. The communication environment in the space environment is not always connected. Communication is only possible when the satellite system, communication satellite, or ground station can communicate with each other, leading to a discontinuous communication environment with long interruption intervals. On the other hand, mobile networks on the ground is not designed for communication with long interruption intervals as in the space environment. As a result, the software we transmitted fails entirely without retaining any intermediate states. Furthermore, when retransmitting, the process had to start from the beginning. For the space environment, the communication data is divided into small chunks, and transmission is performed for each of these fragments. We acknowledge the need for mechanism to collect all the fragments on orbit and then combine them to extract the software. The third is unscheduled application updates. This describes the challenge that occurs after software has reached orbit, once it has overcome difficulties. In the framework tested this time, it was not possible to set the timing for applying the software update after it is performed. As mentioned on page 8, this demonstrates the difficulty of synchronizing the update timing across multiple satellites. We have identified the need to examine such a mechanism moving forward. In this experiment, we examined mechanisms for automated software to achieve software-defined satellite and perform the preliminary test combining an existing software framework with a satellite network. As a result, we have identified 3 challenges to address as we move forward with further examination. The first is the network speed in the space environment. The second is the network characteristics in the space environment. The third is application update timing. We implement a framework for automated software updates in the space environment. Based on these results, we will begin by examining and implementing the necessary functions as shown on the slide. The first is the examination of data management methods between the satellite system and communication satellites. The second is improvement of data transfer efficiency between the satellite system and ground system. The third is examination of update management method for software version control across multiple satellites. This concludes my presentation. Thank you for your attention.
Any question? There's one.
Hello, thank you for your presentation. I was wondering how big is a software update image if you want to transfer it? So is it in the megabyte range or is it in the gigabyte range?
We assume the update size is about megabytes, not gigabytes.
Any other questions? All right. Thank you so much.